Hello, welcome to not another 3-minute video with Nathanael. You want to know why? Because there are only 2 sheets of plastic in front of me. Sooner or later I'll get a whiteboard. Anyways, because this video is going to be in 2 parts. Because I'm going to solve question 2 of MAT Oxford 2021. Now this question refers to what is called a Maclaurin series. A Maclaurin series is basically converting an infinitely differentiable function, you better check that up, into a polynomial, which is a series on something x something, plus something x something plus something x something. Now, the first question asks us to find the value of ln 2. Now, this is without a calculator, so we can use the Maclaurin series given to us. Now, using the logarithmic identity, ln a equals to minus ln 1 over a. So we sub a is 2. Because it says mod x is less than 1, that's why we use half. So 1 minus x equals to half. X equals to half. Now, the Maclaurin series that will be given, summing half into this, will give us and this is just a warm up. Now we bring these powers of 2 to the denominator. Because in multiplication, it is perfectly fine to switch the multiplicants, which are basically the numbers that you're multiplying together. Now, using the identity, minus ln half is ln 2, so that means ln 2 will become half plus 1 over 2 times 2 squared plus 1 over 3 times 2 cubed plus 1 over 4 times 2 to the power 4 plus dot dot dot. Now the second question says, using this Maclaurin series, find k such that k over 24 less than ln 2 less than k plus 1 over 24. You might think that's not very easy without a calculator, but look at this third term. Now look at the term in the denominator. 3 times 2 cubed equals to 3 times 8 equals to 24. There, that's easy. All we need to do is to add these 3 terms up. Now we do the multiplications. Now we give them a common denominator. Of course, you can simplify it to 2/3 if you like, but this number in the numerator tells us what k is. K equals to 16. There you have it, parts 1 and 2 of question 2 of the MAT Oxford 2021 test, involving a Maclaurin series and some logarithms. Now, what are Maclaurin series used for? Maclaurin series are useful to find approximations of many common constants. For example, one time I wanted to find an approximation to ln 2. I used a very unwieldy series, 1 minus half plus 1/3 minus 1/4 plus 1 over 5 minus dot dot dot. And it only gets a decimal place of accuracy every 50 terms or so. But later, when I was doing this, I found out that this series was much quicker. And it's even quicker when you do it in binary and you have a table of reciprocals. Because these powers of 2 are basically just switching the decimal point in binary. So this is how I would calculate ln 2 now. Because when I was younger, when I was still starting out with Maclaurin series, and I love ln 2, I used this series. It took me a while for my calculator to figure it out though. Although the reciprocals are simple, I needed to get through 1,000 terms to get 3 decimal places of accuracy. There you have it, a very quick series for ln 2, and you still wish to calculate it. Bye bye! Okay, now to part 3. Remember the Maclaurin series I showed you earlier? Now let's find the value of ln 3/2. Now this is the value we are asked for. 1 minus x equals to 3/2, so this becomes x is minus half. Now, doing this, and subbing minus half into the earlier Maclaurin series gives... Now notice the signs alternate. It's the exact same Maclaurin series as before, but now the signs alternate. With a bit of luck, we can realize this is the series for ln 3/2. And I can also deduce that ln 3 equals to ln 3/2 plus ln 2. Now we add these two Maclaurin series together. Then we have zeros in the even numbered, and we have 1/3 times 2 squared in the odd numbered, followed by 1/5 times 2, 4, yada yada. So on, here's the series for ln 3. Now, summing up these 3 terms, we can get a good idea of what ln 3 is. 1 plus 1/3 times 2 squared equals to 13/12. Remember the fraction I showed you earlier? This is a great example of fractional arithmetic. Now we add the first 3 terms together. Remember I showed you how to do it? I'm sure you can do it yourself now. What is the answer? Yep, take the common denominator and then do lots of other stuff. And it gives the answer 263/240. Now, I'm drawing this square on the next part. This is a lesson about planning ahead. Now, we can round this up to 216/240 equals to 11/10. Therefore, 13/12 to ln 3 to 11/10. That is exactly the statement we are supposed to prove. Now, we are now facing a really big number duo. You think this can't be solvable without a calculator? But it's actually very simple. If I had used a calculator, which I didn't, 3 to the power 17 will be over twice bigger than the other number. Now, we can use ln 4 equals to 2 times ln 2. Now, we can use the lower bounds that we have discovered, basically. So, we can use this space for working. Good thing I'm saying not big spaces. 13/12, which is our lower bound times 17, equals to, I'm trained for this, 221/12. So, 2/3 times 2 times 13 equals to 52/3. Now we can convert this into something over 12. And this works out 208. This is 3 times 17, this is 4 power 13. Now, this shows that 3 to the 17 is bigger than 4 to the 13. The question asks to justify our answer, and this is what we did. We justified our answer using the identity ln A to B equals to B ln A. There, another logarithmic identity. I just taught you one logarithmic identity in the previous part. Now I taught you another. And now we learn how to compute big numbers and compare them easily using logarithms. Thank you. Bye.